Good morning and welcome to Physics 101. Today is September 28th. We are in week 4 because this is a late start class. We are also in the middle of preparing for an exam. Very good. And I'm hoping that you guys have already started. And actually, I can check to see who started, but I'm really hoping that you guys have started the review because it's of the utmost importance in terms of your exam. And spend as much time as you can on it. I mean, it tells you that you need to spend at least 3 hours. Plan on spending more because there are a lot of topics that need to be covered. Some of them probably they're a little bit intertwined in a sense. It might lead to some sort of confusion. Basically, when I'm talking about waves, have the concept of frequency, the concept of wavelength, and oscillations also have concept of frequency, but they don't have concept of wavelength. And then there is the wave velocity, and then there is sound with its pitch instead of usually normally we talk about the frequency. And then in addition to that, you have the Doppler effect, and the Doppler effect is common to both sound and light and all waves actually exhibit that, in addition to the beats phenomenon that is also included in waves and all waves, albeit when we talked about this ones, we focused mainly on the sound. But it's still, these concepts are also there too for the case of light, and the phenomenons are a little bit different, and they're all coming from the same idea, which is interference, okay? When we went and did the lab, we actually explored light more specifically, and we saw that light, actually the white light, is broken into different waves. Each wave has its own frequency, and that is what the eye sees as different colors. And then after that, we were able to recognize that each element in the periodic table, and as a matter of fact, each compound in general, has its own unique signature, has its own emission spectrum or absorption spectrum, okay? And we focused mainly on the emission spectrum because it was kind of easy a little bit for our case. So what we did, we had several gases and we basically excited them by putting them through tremendous voltages. And then at the end, they emitted light, and we were able to see that hydrogen is different from helium, from neon. And then we actually looked at other spectra, and that's the whole idea with it. So that is really the points up to this point. So this is how the test is structured. It focuses mainly on these things, okay? We saw also optical devices, and that was an important idea because we took the idea of light being going in a straight line, basically. There is a principle I didn't know, we didn't talk about it in lecture or actually in the book also, and the idea is a so-called Fermat Principle that governs the behavior of light, but we use these consequences, namely the law of reflection, that an incoming light will reflect in such a way that the angle of incidence is equal to the angle of reflection. And then we also use the law of refraction. If you have light, and this is true also for all media, by the way, for all waves, I'm sorry. If you have light transiting from one medium to another with two indices of refraction, because basically a medium has its own properties where light can propagate in it with either ease or lack thereof. Some materials, actually, light does not even propagate on them at all, and those are the opaque materials, basically materials that don't transmit light, versus transparent materials that do transmit light, but again, like, for example, water or glass or even other plastic, for example, and other materials that have these properties. So light slows down in a sense in there, albeit that is a macroscopic, basically, phenomenon, but on the microscopic level, light really does not slow down. Transiting from one atom to the next atom, it goes with the speed of light during the moment that it is actually exciting when the atom absorbs that light is not propagating. And that is what gives you the appearance that light is slowing down in that medium. So we looked at that and we saw the law of refraction that gives me basically how light bends when it transitions from one medium to the other. And based on that, we took these ideas and we started making images. So we delve into the image formation. When light reflects on a mirror, you have three possibilities. Either the mirror is flat, excuse me, or it has a curvature pointing into basically you as you're walking into it, or away from you as you go into the mirror. So in other words, the coating could be on the other side and the reflective part is on the inside, or the coating actually is the outside, the inside, and the reflective part is on the outside. That is what we mean by concave and convex mirrors, okay, as opposed to a flat mirror. The image forms in a different way. And we did actually a lab on that on lenses, and also on optical devices in general. And we focused mainly in the lab on the lens, and the lens uses a different thing. Mirrors used a law of reflection. Lenses use the law of refraction, because you have light that comes in, go through the bulk of the lens and slow down in the process and get bent. So when light comes from far away, it all is going to be bent into a single point. That is a focusing lens or converging lens or convex lens. Okay, they're all the same thing. The focal length in this case is a positive number. Or you have a situation where the light goes through the lens and it diverges away from it, giving you the impression as if it's coming from a focal point behind it. So in this scenario, the lens is a diverging lens or concave lens, or a, so that's basically the two non-focusing, if you wish. Okay, so those are the two types of lenses. As a matter of fact, you can combine these two in a sense. You could actually have a flat side and a convex, converging side. You could have actually diverging side and a converging side on the other side. So you could combine these things and make up all kinds of optical devices. One of them is, for example, lenses. The other one is the camera, and we'll talk about the camera. And also the other one, for example, is a telescope or a microscope, the purpose of which are to magnify or collect light and then direct it to a single point where you're going to amplify basically the size of the object. Which brings me to the image itself as it forms. There are several ways. First of all, the image could be upright, similar to what the object is, or it could be flipped in a sense upside down, or it could be, and then the other thing also, it could retain its form factor in the sense that the size does not change. Like when you stand in front of a flat mirror, the image in this case will be a replica of the object in a sense that the size does not change, or it could be magnified, or it could be actually reduced in size. So these are some of the things. The other thing also that we looked at when we talked about the image formations was the image real or inverted? In other words, is there really rays, light going to form that image? Should I bring, for example, a film and expose it? Would I get an image? Or I would not get an image. The film would be completely overexposed and nothing will show on it. That will yield to the concept of a real image versus a virtual image. Simple case, for example, of a virtual image is when you stand in front of the mirror, flat mirror. If you go on the opposite side, for example, and look, you're not going to see another you on the other side, number one. Number two, as a matter of fact, if you go on the back of the mirror and place a film on the opposite side of the mirror, where the image appears to be coming from, there is no rays. Light does not penetrate through the mirror and go to the other side. In other words, the film will not produce an image. It's going to be just exposed, and that's the end of it. It's going to be burnt. There are some images that form really, for example, excuse me, when we did the lab, we had an object, we have a lens, and then we have a plate, and on the plate you could actually clearly see the image forming on there, okay? And provided that the object is at least further away from the focal length of the at least more than the focal length of the at a distance more than the focal length of the lens. So the image forms really there, and you could see it. So if you put a film in there, the image will be burnt, and you're going to produce an image. It was upside down, okay, and the image was real. In other words, it was inverted. And then depending on how far it is, it could be smaller in size. Now, when you bring it behind the focal length, then in this case, you could form different images. Actually, the image forms on the opposite side, and you can't see it. You cannot put a film in there, and it's not going to produce. So it's a virtual image. So these are the concepts that we covered up to this point, and these are the concepts that you're going to be tested on. So I'm hoping that you guys go through the materials, understand what is going on, understand the concepts and how they're actually related to these things. And then you have a lot of materials, as a matter of fact, to go through. So I'm hoping that you guys spend the dedicated time for it and maximize your grade come next time, next Wednesday when we're having on that day. Now, here is the deal. Since we have an exam on Wednesday, a week from today, and because some of you might not really find the time to do it after the exam because you either have other classes, or you may be even having work to do, working, or you may even have related matters, family matters that you need to take care of. In that situation, you have this time that is allocated for the class to take the exam. So I will be on the computer. Should a problem arise, I will be more than happy to help you with it. And there will be no live session a week from today. So on Wednesday, October 5th, there will be no live session because you're going to be taking the exam, okay? And if you cannot do it during daytime, I know a lot of you are actually not watching this one live. They watch it recorded later on, because you're working in the morning or you have classes. Some of you are probably in high school, so you still have to be on campus in the high school, and you cannot take this class live, you cannot attend live. So in that scenario, you still have the evening. So there is no excuse. In other words, we cannot extend the exam past that day. So if you cannot do it during daytime, you can do it during the evening, and preferably you do it during this time and you're done with it. Go through the review. You still have plenty of time to do it. There is ample time to do that. You have the weekend that is coming. There are a lot of concepts to be covered. As I promised, you will get full credit the minute you submit your review, regardless of what your score is. You could score 1% in the review, okay, and you still get 100% for the review. Obviously, that is going toward your participation in a sense that you're engaged in the class and you're doing what you're supposed to do to pass the class, okay? So this is what I have to say about the review, and it is very, very important. So everything else at this point, I know we're supposed to do motion and we continue the topic we started last time on Monday. And that is important, but not as important as the actual exam, which is do this one. Now, there was a question that came about the lab. Lab is not canceled. Just because we have the exam on Wednesday, lab is still on Monday, okay? So lab, as a matter of fact, is never canceled, so they take it from me, unless something happens to me terrible that I cannot make it to campus, okay? And even then, I will try to see if I can make it still. The point being in here is, if that happens, then I will see if when we have enough faculty on campus to come and sub for me. So even then, still, very likely we still have a lab. So in other words, lab is always in session until the end of the semester, okay? For that, please review the syllabus for exactly what we have to do every Monday when we meet. So Monday, October 3rd, we still have lab. And as a matter of fact, we have also a live session on Monday morning. So we still have work to do. We still are going to get into Newton's laws of motion on Monday. So we still have materials to cover by then. And as a matter of fact, next week, albeit we have the exam, you will also have a homework assignment, and it's going to be due the week after. Okay, so I just wanted to make this one clear. And I also were going to send a message. I know you received already enough warnings and messages and all kinds of things, information and reminders and things like that from me. But again, you're going to receive another reminder, especially pertaining to this item, because there was a question about it, whether or not we will have lab or not. No, we will have lab all the time, regardless of what we have. And this is why, as a matter of fact, I chose, I know initially we said about the week of the 3rd, and that is why initially why I changed the exam date to Wednesday, so that it does not interfere at all with our Monday plans, which include a big chunk of it, which is the lab on that day. Okay, So this is how things are. So which means that the next exam is going to be, I would say 99.9% is also going to be on a Wednesday, and we'll do that until the final, which is we will not have labs on that week, the finals week. Then at that point, and that point only, where we can do exams on Monday. Okay, so this is the whole idea behind it. So I'm hoping that everybody is clear in terms of this. And as I promised, I will follow up with other reminders so that you guys know these things. Okay. I hope that I covered enough things for this exam. I don't really mean to make a big fuss over it, but I usually do because it's important. Okay. So let me share with you the screen. Share, if I can find it. My notes. So we're still dealing with the motion. Last time we introduced the concept of motion. By the way, when somebody tells you motion, the word motion is equivalent, it's not exactly equal, but equivalent to velocity. You have motion if you have velocity. If you don't have motion if you don't have velocity, basically. When the velocity is 0, the object is at rest. Period. When the velocity is not 0, the object is not at rest, we say it's moving. So this is connection. So you have an object in here, and this is its velocity. So if I say an object has velocity, I mean it is moving, it has motion, okay? So when the object does not have velocity, the object is not moving. So this is a clear-cut connection between the two. So when a person is talking about motion, they're talking really about velocity, okay? And how much velocity you have. Now, having a velocity, it could be positive, it could be negative, it could be anywhere that it could be pointing. So it's really a vector. Okay, and the motion also has direction. Okay, so this is really what I'm talking about in here is the magnitude of the velocity, the speed, if you wish. Okay, the speed, if you have a speed, you're moving. If you don't have a speed, you're not moving. Okay, that is clear cut. I hope that is clear to all of you guys that this is two connected. So introduce the concept of velocity and the concept of speed, actually, before getting into concept of velocity. Concept, constant. Concept of velocity is, by definition, the rate at which position is changing with respect to time. That's in a nutshell what it is. Provided this time in here is taken very, consecutively first. Short time, basically. Extremely short time. That's how your speedometer does that. If it's not, then you have talking about average velocity. I may give the example that, okay, you start from, you go to work, it's 30 miles and you drive for an hour. Your average velocity in that case is 30 miles per hour. What is it? It takes you, let me go back to the example that I mentioned. So the distance between your place and work is 30 miles, okay? Yes. And it takes you 1 hour to drive that distance. So in this scenario, your speed, your average velocity, I would say it's 30 miles per hour, okay? So it's an average velocity in here because part of your trip will run you through the red light and you're slowing down. Part of your trip also will give you in a zone where the speed limit is 35 miles per hour and you could go 35 miles per hour. So at some point you're going faster than the average. Some places you're actually doing 40 or 45 miles per hour. So you're more than the speed limit. And in other places you're completely stopped because your red light is red. So you're waiting for it to turn green. So in that case, your velocity at that moment is 0. But your overall velocity is from when you basically leave home to the time you get to work. That distance is 30 miles. So that's what we mean by delta x. And delta t in that case is 1 hour. So I would say 30 miles divided by 1 hour. Now in that case, it's easy, 30 miles per hour, okay? Simple enough to do. But what I mean by this ratio in here, so in that case, we dress it with a bar on top of it. It's going to be a V bar, okay? We put a line on top of it. That's what I mean by an average in this case. It's an average. In some other literature, and probably some of you are actually going to engineering, you will see this bracket, curly, basically brackets that you have them on your keyboard, the less than and the greater than symbols, okay? They are under the, for the Windows keyboard, they're under, next to the M, basically, under the letters L and K, okay? So that sometimes you find that one in there, okay? Yet in other literatures, and it's probably more explicit that way actually to write it, you could see it V and right next underneath of it AVG for average, okay? So it's all of it the same thing. So that is what I mean by in this case is that the span of time that we're talking about, the lapse of time that we're talking about in here is long, okay? When this time is extremely short, then we're talking about the instantaneous velocity. Some of you are actually going into engineering and you will be introduced to more advanced classes in math called calculus. And that is actually what the calculus is. You take this limit and you make it as small as possible, almost zero, not zero, because you can't divide by zero. Okay, algebra prevents you from dividing by zero, but you make it extremely small as it can get. In that case, you're dealing with an extremely small infinitesimal called quantities. That is where calculus is emerged from. That is where calculus is coming from, okay? So in our case, we really don't care about that. For a speedometer, for example, in the car, let's say, for example, it's taking readings every 1/10 of a second, 1/10 of a second, so be it, that's fine, okay? So that is how we're going to find the velocity in that case. It's going to, I mean, by the time you look at the speedometer and you raise your eyes from it, the speed probably has changed. I mean, it's just fluctuating, okay? Going up and down, because it's doing a lot of readings in that span of time, okay? So this is the velocity that we have introduced. We also introduced the concept of acceleration. So the acceleration in a similar fashion is the rate at which the velocity is changing with time. So now, how is the velocity increasing or how is the velocity decreasing? That depends on this ratio. Again, I'm assuming that this time is extremely small. If it is not, then I'm talking about, again, the average, okay? If delta t is finite, namely the span of time or a lapse of time is finite, then in that situation, we're talking about an average velocity. So these are some of the average, acceleration in that case, because that's how the velocity changes. So if you have an acceleration that is 0, then that means that the velocity is not changing. It's the same. Because from this equation, you will have 0 is equal to the change in velocity over the lapse of time. If the lapse of time is finite or small, extremely small, it doesn't matter, because that means that this is 0 also. That means no change in velocity. Okay. If the acceleration is not 0, so this is if, and this is another if, that means then immediately that the velocity changes. The book introduces the concept of a jerk, which is the rate at which the acceleration is changing, but that's not used in science and physics, at least. Okay, so we really don't use that concept. I know it's a concept that is introduced by some mathematicians, but in terms of laws of motion, it has no bearing. It has no consequence. So we really don't talk. We don't really mention it at all. So we just focus on these things that are connected to the laws of mechanics or the laws of physics. So that's it. That's all we need, really, in terms of that. I know we talked about the acceleration in the same direction. The object is accelerating. When the acceleration is the opposite direction, the object is decelerating or slowing down. Okay. So these are the concepts we covered up to this point. And I mentioned Mr. Galileo. Mr. Galileo, actually, here is a question that was raised before him, and it lasts for about two millennia, okay, about 2,000 years. people believed, based on the philosophy, based on Aristotle's work, that for 2,000 years, that is, that the state of an object, if you take an object and you put it somewhere, it's at rest. So objects tend to be at rest. For example, I have this object in here. If I put it on my hand, it's going to stay on my hand. As long as I don't move my hand, it's going to stay there. If I put it on the table, it's going to stay on the table, and it's going to stay there for whatever time I decide that it stays there. If I come and push it, it's going to move, but then it's going to stay back, to go back into its rest. So objects tend to be at rest. That's the belief that people had before Mr. Galileo. Mr. Galileo challenged that idea. Okay, there's a lot of noise outside. I'm sorry about it. So Mr. Galileo challenged that idea and basically reasoned, because here is the thing: if I take this object, according to Galileo, and move it, the object will move and then will slow down and stop. If I push it more, the object will actually move more, but then it's going to also stop. No matter how hard I push it, it's going to ultimately stop. Okay? If I push it a little, it's going to barely move, but at the end, it's going to stop nonetheless. So that is the argument that Mr. Aristotle put, that objects tend to stay at rest. Okay? No matter what the shape of, even if you bring it as a spherical object and you push it, it's going to move more than an object that is, for example, the one I was drawing all along, which is like a cubic shape. Now, when challenged by that idea from Mr. Aristotle, why some objects take longer to slow down and stop than other objects? Obviously, the shape is not the answer to that question, because I could take two spheres, okay, and push them with the same force. One of them will slow down and stop before the other one, okay? If they're of this identical materials, this will actually continue longer, the bigger one, as long as I push them with the same speed, okay, with the same force. And this one will actually stop first, okay? So it's not the shape. How about the mass, okay? Does the mass matter in this case? Okay. The mass will matter, but if I bring two similar size objects, okay? I'm sorry, I'm talking about the size. Two similar size objects, but they are different materials. Then also, the one that has more mass will continue, and the one that has less mass will slow down and stop immediately. As long as I push them with the same force. Don't be confused with the experiment where the lighter object tend to move further, because you move it actually more, you give it more force because it yields faster. So you have to be careful with this thing when you do it. Here's the point in here. I may have said this wrong, okay? I'm sorry about it. Okay? I think it's the other way around. The point being in here is the shape doesn't matter. You can eliminate the shape. You can eliminate also because the size then will matter, depending if you have different shapes, just change the sizes and you will see that the experiment changes. So the size also, you can eliminate the effect of the size. So at the end of the day, really, the experiment that Mr. Aristotle basically his approach to this is that, look, I think there is only one and one only reason for that. And the only reason for that is some objects inherently remember their state, and some can remember better than the others. That's basically his argument, okay? It doesn't make sense. I know it's like kind of a nonsense at this point, but that's his argument. Mr. Galileo, when he did his experiment, this is how he did it. He took an incline, okay, small incline so that he can control his experiment. And he took a marble and he documented where the marble is dropped from, okay? The marble, as it falls on the incline, will go on the flat surface and will stop ultimately, okay? So what he did next was he's made the surface smoother. Okay. And he dropped it from the same height. And he noticed immediately when the surface is smoother in the second experiment, the marble will move further before it stops. So he even made it smoother even more. So in each situation, as he increased the how smooth the surface is, made it less resistive, basically, the marble will continue forever and ever. So Mr. Galileo argued that if it were not for the friction between the surface and the marble really should not stop at all. It should go forever and ever and ever and ever and ever. So that is his reasoning. So we really need a force, and that force is provided by the friction here to make an object stay at rest. Otherwise, the object is not going to stay at rest. So Mr. Galileo argued that objects tend to be at motion. So motion is the preferred state of an object. So objects are, how should I say it, is tend to move in the same direction. They don't change the direction and with the same speed. Namely the same velocity, because remember, direction and speed are the vector velocity. That's his argument, because all you have to do is eliminate the friction that is making this marble to slow down and stop, make it less and less and less and less, and you will see my point. So he theorized in a perfect world where there is no friction, this marble will go forever and ever and ever and never slow down. It stays in the same direction at all, unless you come and put an obstacle to it or put another force to make it go in another direction, then that's going to change. So that is his argument, Mr. Galileo. More than that, with the experiments of the incline in here, he was able to find this force that caused it to move at all, which is the force of gravity. And he measured the force of gravity, the acceleration due to the force of gravity, because if you put a bigger marble in this case, or doesn't matter, the mass of it is going to always follow the same path. So he found, of course, if you make the inclination more, it's going to fall more. If the inclination is less, it's going to go less. So the little bit of trigonometry, which was known from the time of the Greeks. Mr. Galileo was in the 1600s, so he knew about the trigonometry at that point. He was able to find the gravity, the acceleration due to gravity, to being g equals to 9.8 meter per second squared. I mean, it changes depending on the elevation. It changes depending on how far you are from the oceans. But on average, depending also on the equator, how far you are from the equator. But on average, it's about 9.8 meter per second. So g is equal to 9.8 meter per second squared, or per second per second. So that's basically one of his things that he also found. This is, by the way, where the lab was last time, if you guys remember, when we did the gravity. So the lab was this, if you guys remember. You had a magnet in here, an electromagnet in here, and that was connected to the power, and then you have a rod that was holding it. And you also, actually on the rod, there was a line in here for a power, for a current, okay? And there was another line behind the strip, basically, that was recording the different positions of the mass that you dropped from here. So there was a mass in here. When you kill the current, the voltage, so the electromagnet will lose its electricity, and then it stops from becoming a magnetic, basically, it loses its magnetism. This is a concept that will explore down the road. Actually, it's following Ampere's law. But the point being, in here, you have no magnet, so this will fall in its own. In the same time, you were holding into pulse generator that was generating 60 pulses per second, basically firing 60 times per second. Obviously, the whole fall took less than half a second. So basically, fired only about 30 times. That way, I had about 27 points. Yeah, some of you have probably a little more, 28 points, but some of you actually, because they let go of their of the pulse generator, so they missed some points in between, and they had about 20 of them. So the point being in here, it lasted for about half a minute to drop. About 30 seconds. No, half a second. I'm sorry. I'm getting a little bit messed up in here. Not correct. It lasted for about half a second, not half a minute. Okay, half a minute. So you have to drop it from a very high building in order to do a half a minute. So anyway, it dropped, and that basically you recorded the data. So what you have in that lab in here, if you guys remember, every time it fires, it's going to give you the position. Initially, the spacing between the different pulses was small. As the object starts to fall, the spacing gets bigger and bigger, meaning it's going to cover more and more distance for the same lapse of time. Remember, it was firing 60 pulses per second. Okay, so the time between each recording is 1/60th of a second. This time also is the same span of time, 1/60th of a second. This is also the same span of time, 1/60th of a second, and this is 1/60th. So the time it took to travel this distance is the same time it took to travel this distance. It's the same time. The pulse was generating bang, 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 60 pulses per second, okay? So in this case, what you have a depiction of the position of the mass as it was falling for an equal amount of time. But the distance traveled in this case is less than this distance. Clearly, it was moving faster in here than in here. So it was gaining speed. And when you went and did the experiment and plotted the data in here, you guys remember this is the time and this is the position. It was more or less like this one. So the position in this case was increasing. So this is your height, y, and this is position time. It was increasing in what looks like a quadratic function. And it is a quadratic function, as a matter of fact. And then when you plotted the velocity, where you took 3 consecutive points and you added these 2 distances and you divide them by the lapse of time, which is twice 1/60th, which is 1/30th of a second. And you divided by that number, you found the velocity, and the velocity, when you plotted it, or I know some of you probably, no, I think all of you did. So when the velocity was plotted, it should really have been a line. Some of you had a y-intercept in it, but that's fine. I mean, the ones who did not complete it because they were going to do it in Excel, and that's fine. So the velocity in that case is a line. The slope of the line, which is the ratio of the rise over run, that is actually the acceleration. In other words, this velocity, if you put it in Excel, is some acceleration times the time plus some initial velocity. Obviously, the initial velocity really should be 0, because when you kill the voltage, this mass was not moving. I know the numbers are not going to match exactly and give you a 0, but that's the point in here. Theoretically, the initial velocity is 0 because you dropped it from rest. But if you notice it was wobbling already, I mean, you can't really have it completely at rest. There is that jiggling motion. Furthermore, if you let go of it immediately and then you start recording, you miss the first point and you already are going to record starting from this position. So there was an initial velocity for some of you, either because of an error in handling the pulse generator, or because of the fact that it was wobbling. And this number was very, very tiny anyway, okay? Extremely small, but it's still there, not 0. That's part of the error. The other thing also, when you measure the value of the acceleration, you found it very close from, some of you found 9.7, some of you found 10.1, I think, and so anywhere in between, some of you 9.9. It should really be 9.8. Obviously, all of these units are meter per second squared. As a matter of fact, you were asked to compare it to the experimental value, to the known value by Mr. Galileo, which is 9.8, and tell the error. Some of you were 0.5% error or less, and some of you had big errors. So, okay, so that depends on how you handle the pulse generator. The other problem that I saw with some of you guys were that spark that was generated toward the bottom, and it kept trying to get to bring it up so that you don't generate that spark. It adds to your errors. And then when it bounced back, the spark was still, I mean, the data was still collected. So you needed to avoid that region anyway. And the other error is actually by using the ruler and finding these distances, okay? These distances. And there are some errors that you really cannot control, because that pulse generator tells you that I'm firing 60 pulses per second. That is actually built into, should really have errors in it too. I mean, you can't control that. That's the device that was given to you, and the only thing you can do is live with it. But that's interesting because you basically replicates the experiment of Mr. Galileo. Okay, and in doing so, you found the same value, or experimentally it should be the same value anyway, as close as possible from it. Some of you were very, very close from it. Some of you had 1% error, and that's expected. I mean, at least with the equipment that we have, we don't expect to do better. And note that Mr. Galileo did not have a watch at that time, and he used actually his pulse to find this value, okay? So this technique that you guys used is called the Thromboscopic Method. Actually, it doesn't use really this electricity. For the stroboscopic method, you use a camera, okay? You have a falling object or object in motion, it doesn't have to be in falling at all. And you can send light and turn it off, on and off, on and off, on and off. And each time it goes on, it takes a picture, basically snaps a picture of the position of the object, and then gives you an image similar to this image that you guys took with you home, basically of the different positions, okay? It's similar to when you're looking, for example, at some of the tires that are moving super fast, or bicycles, for example, or even some of the cars that people have them on their wheels. Let me pause the recording, guys, okay? Because I kind of am annoyed with this thing in here, and I'm going to close the window. Okay, hold on, okay? I hope that's better because the noise was so much. Anyway, so that is actually the method that the book talks about, and some of the homework problems actually refer to. So I'm hoping that you have an idea at least of how that is produced, and it produces those images in a sense that basically tells you how the different positions of the object are, okay, at different times. So let me continue sharing. Share. So this is basically in a nutshell what we have done so far. Okay, at least for the labs and all. Okay, and that's a good review actually for the free fall. Okay, that the whole lab was on the free fall, because I'm assuming that the object was not subject to, for example, air resistance. Theoretically, also that also comes in as a problem for you guys. I know we were in a lab environment and we really didn't have a lot of moving air, but the presence of the air itself will alter your experiment. So the values that you get for the acceleration are also impacted by that too, okay? Ideally, you should really do this experiment in vacuum, okay, to eliminate the presence of the air. And that is basically also one of the effects that we have seen, okay, in there. Okay. So this is about the free fall. Now, if the object is actually thrown with an initial velocity, so if you throw it upward, for example, with an initial velocity, it's going to start to move up. In doing so, it's going to slow down. Remember, the gravity is always pointing down, no matter which way the object is moving. It's always pointing down. As the object is going up, then the gravity is pointing down. So in this case, it's slowing down. It's going to stop at some point and return back and come back, okay? And as it does, it's going to gain that velocity back again, because at that point, when it stops, it's moving down and the gravity is pointing down. So in this case, it's going to accelerate, okay? So this is basically in a nutshell what's going on with that motion. Now, note, in an ideal world where there is no friction, the initial velocity with which you throw the object in must be the same impact velocity as long as you are on the same height. If you go on a cliff, for example, and you send an object upward, it's going to rise, okay? And as it falls, the minute it passes by you, it's going to pass by the same speed as you throw it up. But then it's going to still keep on gaining more velocity. So when it impacts the ground below, it's going to impact with even a greater velocity. How much it is, you say? It's easy, okay? Let's say, for example, for the sake of argument, we spent it with 15 meters per second initially when we throw it up, okay? After 1 second, I'm going to take the value of G to be 10, okay? I know It's 9.8, but I'm going to approximate it to be 10. So that's the value of G. That means that every second, I'm going to either lose or gain 10 meters per second. That's what that is, okay? So after 1 second, and since the object is going up in this direction, I'm going to lose 10 meters per second out of my 15 meters per second. So in this case, the object is going to rise from here, go up. After 1 second, the object will drop its velocity. It was moving 15, remember? And this is after 1 second. This is 0 second. This is the starting. This is 1 second. So now the object is actually only moving 5 meters per second. That's it, because it lost 10 of them. 15 minus 10 is 5. So I'm left with 5 meters per second. Now it cannot travel all the way up for another second. Actually, after half a second, it's going to lose the other 5 meters per second. In other words, after half a second, the object will lose half of a 10 meters per second, which is 5 meters per second. Since it already had 5 meters per second, it's going to stop right here and there. So after another half second, in addition to the first second from the initial motion, now the object has 0 velocity. It stopped. It's not moving anymore, at least upward, okay? So at that point, the object is at rest. But then now the velocity is 0 at that instant, and the object is under the force of gravity, which is pointing down 10 meters per second. That's the acceleration. So it's going to gain a speed. So after 1 second, it's going to, this is 1 full second, it's going to be moving downward with 10 meters per second, because it started from 0 from the top, and now it's gaining per second 10 meters per second. So now after 1 second from coming down, it's going to be here with 10 meters per second. Now, obviously, the ground is rushing, coming to meet it. And by the time it impacts the ground for the rest of the other half a second, it's going to gain an additional half of a 10 meters per second, meaning 5 meters per second, to impact the ground again at 15 meters per second. So if you're asked, and I think this is one of the questions that you're asked, as to how long does it take for it to go all the way up and come down? It's going to be 3 seconds. Why? Because going up, it's 1 second plus half, that's 1.5 seconds. Coming down, it's 1 second plus half a second, it's 3 seconds. So it takes 1.5 seconds to go up, stops, then another 1.5 seconds to come back down. The total time is 3 seconds. This is the time of flight. Meaning the time it stays in the air, suspended in the air. Think of yourself as, who's the famous basketball, James, what's his name? The basketball player now? I don't know much basketball, okay? I'm sorry, guys, I'm kind of a soccer guy, okay? I was going to say Michael Jordan, but Michael Jordan is a long time ago not playing. So think of a basketball player. The minute that they jump up, they're suspended in the air, and then they dunk the basketball and they come down. That is the time of flight, how long they are going to suspend it. Actually, there is an illusion in here, and that is they seem to be suspended in the air, because here is the thing. It takes them about 1 second to go up, and then another second. I'm talking if they jump with 15 meters per second, okay, depending on how fast they jump, okay? Because they might stay suspended even longer if they jump harder than that one. And then they're going to slow down, and they're going to come back in here, okay? So for a total 1 second going up, and actually another second, so a total of 1.5 seconds there before impact, okay? So they spend most of their times basically in the air. And they look like they are frozen in the air actually for a moment, okay? Yeah, 1 second or 1.5 seconds is not much time, but the jump itself, the initial jump, and then it's slowing down, stop completely. So this is a complete stop, okay? and then starts coming down. So again, this is an illusion, but that's related to the same thing that I was talking about. Granted, the fall is at the same point where the object started from. If the object falls further down, like for example, as I was describing on a cliff, then in that scenario, you're going to gain more speed, depending on the height in here, okay? Depending on that height. So this is the free fall. I mean, it's interesting to know how high the object is going to go, okay? If I know the initial velocity, you can find actually the height also, okay? How long it's going to go up, and then from there we're going to use actually this quadratic representation to find the height, okay? This is, remember, this is the displacement for this case, as it depends on the force of gravity in this case, or the gravitational acceleration. So this is the free fall as we described in this case, and we talked about the stroboscope. And this is actually the entire chapter that we have in here for this chapter 2. Okay, I think we went through it extensively. We still have more than half an hour. So let me first of all introduce the stuff from chapter 3, and that is Newton's laws of motion. What I was describing up to this point is the motion itself, okay? And we did it in a simple case, which is the one-dimensional motion. All of this is only one direction, up and down. I mean, if you talk about a projectile, for example, and I mentioned the example of the basketball player, for the basketball player is more like a projectile, actually. Here is the hoop, okay? And usually they jump like this. They don't go up and down. They don't come immediately under the net and they jump up and down. So that is actually a projectile motion. He is moving up, yes, but he's also moving in the horizontal direction. So that's a projectile. So we're going to leave that for a moment later on when we introduce the two-dimensional motion, because that is actually an example of a two-dimensional motion. But I think we're ready also to introduce the laws of motion. Okay, there are three of them, three laws. Newton, when he introduced them, there are three laws. Number 1, 2, and 3. Number 1 law is this thing that Galileo came up with. Okay, this is the first law of Newton, which is verbatim. By the way, Newton was born in the same year when Galileo passed away. So it's in the 1600s. So it's verbatim what Mr. Galileo has done. So the first law says basically, if an object is under, I'm going to put it in caps in here, okay, no net forces. Whoops, what did I do here? And there are no net forces. Okay, the object will move with constant velocity. Meaning, what I mean by constant velocity, meaning it moves in the same direction with the same speed. Okay, velocity meaning constant velocity, constant speed, that is, plus same direction. Okay. I'm going to refer back to this example in here because it's important, okay, that we need to come back to it, because very, very important to understand what's going on. I mean, like, this object is clearly not in motion. I mean, it's not moving. Okay, I can put it on the table and it stays there. But again, it's really moving. There is nothing that is not moving, because think about it, the Earth actually is spinning. So you and I were sitting in here and we're talking, and basically, I know I'm talking in front of you on the screen, and you're sitting on the other side of your screen. Basically, you're sitting or standing or basically laying on something. It doesn't matter. The point being, in here, you look like you're not moving, but we are actually moving. We've been moving tremendously with tremendous speed. The Earth spins on its axis once a day. That means that we go around the Earth once a day, all of us, 24 hours, we go 40,000 kilometers. Take 40,000 divided by 24, you will see how fast you're moving, and you're moving tremendous speed. Last time when we started this class, we were on the other side, basically, on the west side, and now we're moving toward the east side, okay? Rushing to meet the sun on the other side, okay? The Earth. Anyway, the point being in here, we're moving, okay, around the axis of the Earth. The Earth actually is also moving around the sun. Remember, the Earth goes once around the sun once a year. So that is actually another motion that you have to take into account. And then the entire sun is moving around the galaxy, and the galaxy is drifting in the versus the background of the galaxy. So everything is moving. There is no thing that is stationary. So that's why the idea of Galileo that this law is based on is true 100%, that the objects are actually tend to be in motion. Now, the idea of a reference frame, because from my vantage point, this object is not moving. I put it in front of me and it says that. Why? Because I am moving and the object is moving. So both of us are moving. So in this case, the distance between me and that object, the position, namely the angle and all of that, they don't change. So in this case, the object is at rest. So now it's going to be the reference frame that is the issue. Okay. My vantage point, that is true. Because if you're sitting in your car, as far as you're concerned, you're at rest. The car is moving, but you're sitting in it. The car, you're not moving in the car. As a matter of fact, you can take your cup of coffee and put it next to you, and it's not going to spill if you have the cruiser on, if you have the cruise control on, and the road is smooth. So in that scenario, you are at rest because you look at the cup and it's not even spilling. It's sitting in there. You can have it filled to the brim if you wish, and it's going to stay there as long as it's as smooth drive as you can get. The minute there are bumps, then in that case, you're not at rest, okay? With respect to the framework of the car. I mean, the only reason why you don't suspect that the road actually is not unfolding before you and moving in the opposite direction, and the trees are actually moving in the opposite direction, and everything else is moving in the opposite direction, is because of a bias, that's all. Because you would think that who is going to go and move all of the mountains and the trees and the cows and the houses and the road signs and everything in the opposite direction just to accommodate me moving in the forward direction. So that is really, it's a bias. Other than that, there is no experiment, if you're moving at constant speed, to detect if indeed you are the one moving forward or everything else is moving backward. This is it. So that is the first law of mechanics. The second law and the third law, I'm going to defer them next time when we meet, which is on Monday, when we're going to talk extensively about them. In terms of usefulness, it's going to be the second law that is going to be heavily used, and then followed by the third law, actually. So those are the things that we need to talk about next time around. The reason why this is important to talk about it now is because we just basically saw what Mr. Galileo did, and it relates to it. It is actually the work of Mr. Galileo, no more, okay? That is the first law of Newton. He took the work of Galileo, and he put it verbatim in there. Obviously, Mr. Galileo was not interested in the causes of motion. He didn't care about the forces. He was just interested in describing motion, that's all, which is kinematics. This part, the branch of mechanics, is called dynamics. Dynamics really is trying to understand what causes motion. And that is where Mr. Newton came in. Mr. Newton was interested in trying to understand what are the reasons for objects to change their motion, in other words, the acceleration, and what are the reasons for them to basically stay at rest, and how can we achieve equilibrium, and so on and so forth. So Mr. Newton went a step beyond what Mr. Galileo did, and he wanted to have a full understanding of the motion and its causes. So let me go through a homework assignment for this week, okay? I'm going to stop sharing this screen, and I'm going to go through the problems in here that I have, select a few of them for you guys, okay? They're on page 32, so we should be in good shape. So let me share. Let me first of all find the homework assignment for this week. Actually, I'm sorry, they're on page 30 and 31. They're kind of simple homework assignments. So let me go back into share. So these are what you have assigned, what you are assigned to do on these pages. Okay, so they are kind of easy compared to especially the problems from before. And they focus mainly on the concepts that you're going to be dealing with in this chapter. And you're supposed to submit one of those assignments, okay? So you're supposed to submit them, and you have until Saturday, not this Saturday, not October 1st, but October 8th to submit them. So please take care of that. Now, if you have more problems to submit, if you're interested to understand others, that's fine, okay? So I'm gonna go a little bit on to see if I can do 3 and 4, okay? And so those two, because they're related. And then see 25 and 26 and see if we can answer those. And basically that should be it, okay? Because I'm hoping that the idea that we did in the lab will follow through into here, okay? So they're kind of easy. And if you have difficulty with any of these, please let me know, okay? So I'm gonna share the screen and let me create a new page in here, which I'm gonna call problems. Okay. And because I need to come back to the other page in there. So, okay, and let me change the pen color also, a normal color. Okay, so what I said I'm going to do in this case is I'm going to do 2 and 3. Oops, Control-C. And 25 and 26, okay? So they should be easy enough for you guys to be able to understand them and do them. And again, if you choose to submit something else, that's fine, okay? The point in here is I need to see understanding. So for 3, where does the bolt shown in the following strobe drawing have the slowest speed, okay? So they have pictures for you. For this one, you really need a ruler, okay? I don't have I mean, I have the book, so I can technically use a ruler. So for the screen capture, if you're doing the one on the book, there are actually rulers also that you can use and measure the distances, okay? So you have you have an object in here and another one in here, and then I'm trying to replicate it in here, and then it starts to get closer and closer. And at some point, it starts to increase again, okay? What I need to do is find the furthest points in here, okay? If this is stroboscopic picture, similar to the lab, basically, meaning the time it takes to go between 2 different positions is the same. So if this is 1/60th of a second, this too is 1/60th of a second. Okay, so that's basically in a nutshell what that is. So I'm going to take the ruler and measure this distance and also measure this distance because I suspect this one is longer. And then after that, if this is longer, then this is going to be the longest or the fastest when the object is the fastest. The object is moving the fastest. Okay. So when you did your lab, if you notice also the spacing gets bigger and bigger and bigger and bigger by the time for the same time between the 2 consecutive ones. That means that it's moving faster and faster as it gets along. And initially the spacing was small. Okay. And then if you look at the second drawing, is actually easier. It's similar to the lab actually for the next question, which is problem 4. So it starts smaller and then it starts to increase and increase and increase. So obviously it's going to be the last 2 points because that's going to be the furthest one. So that's what's moving the fastest, okay? For 25, in the following strobe drawing, which object if either has the greatest acceleration? Now we're going to study the acceleration. You have to be careful now, okay? So this is for 25. Again, for position A and position B. Okay. For position A, if you notice there, actually the spacing is the same. It's tricky. You really have to understand what you're doing in this case. So the acceleration here is actually 0. Why? Because it's moving from here to here with the same speed as it's moved from here to here, with the same speed to move from here to here, and the same speed to move from here to here. So does the velocity change? The velocity is constant. Okay, so if the velocity is constant, that means the change in velocity over the change in time is 0, because the velocity is not changing. It doesn't matter what time you're going to take it. Are you going to take this instant for the velocity, meaning I take this distance and divide it by the combined time, and then subtract from it this distance plus this distance divided by the combined time? It's going to find the same number. So when you subtract the two, you're going to find 0. So the velocity is not changing. That means the acceleration is 0. So every time you find that the velocity is constant, that's it. You don't have to do much, okay? All you have to do is find the position of the object standing the same. So meaning it covers the same distance over the same span of time. And remember, this is stroboscopic picture, so these strobes are coming at the same instant, meaning that they spend the same time, similar to the lab experiment. So the velocity is not changing because it's covering the same distance. As a matter of fact, this has a name, this type of motion. This is called the uniform motion. So in a uniform motion, the acceleration, the velocity is constant and the acceleration is 0. It doesn't change. So the acceleration is 0. Here is a question, and this is a trick question, so you really have to be careful with it. If you look at the B, the spacing is bigger. So here is B, A, and then A, and then the next position, and the next position, and the next position, and so on. Also, the spacing between two consecutive ones is the same. So this is also another uniform motion because the velocity is the same. Albeit this velocity is more than the first velocity. This object is moving faster actually if the strobes are coming at the same time. Meaning if it's 1/60th of a second, each and every one of them, this covers more distance on that same span of time than the first one. So the first, this also has this similar acceleration. It looks like this one is covering more space, and it is true. So it's moving faster, but it's not gaining speed or losing speed. So I can't really say that it's accelerating. So both cases, they're coming with a 0 velocity, okay? And if you don't believe me, take a ruler and measure the distances, and you will find that the distances are the same, okay? For the next problem, also you're given the following strobe drawings represent the motion of two cars, A and B, okay? During which interval of the motion of the car is the average speed of a car approximately equal to the average speed of car A is equal to that of car B, okay? So during which strobe? So what we're going to do in here is we have A and we have B. So this is car A and this is car B. Okay, so initially this car A covers this much distance in the same strobe, and then this is car C, it goes from here to C, and then D, and then E. Okay, so these are different positions, and obviously from the other one is actually going at a uniform speed. Okay, the distances are not changing. So the point being in here is, the question is, during which interval of motion car A is the average speed of car B, basically, how fast it's moving. Obviously here it's moving very slow compared to car B, okay? Because it covers a lot less distance than car B. Here it's moving a lot faster, okay? And actually, I'm sorry, the D in here, I drew it a little further, it should be here, okay? So these are, they labeled them. This is A, B, and C, and D, okay? From B to D, it's approximately the same speed as this one in here. In other words, if I take this distance in here and this distance and compare them, they're very close from each other. Okay, so during the passage from B to D, car A is moving with the same speed of that of car B. So what happened in this case is car A started. When it started, it was moving slower, and then it started gaining speed. At some point, the interval between B and D, it was moving as fast as car B because car B was moving with constant speed. It's not changing. Then it moved faster. So not only, so it was moving slow, the other one was continuously moving at constant speed. It's not changing. This one started slow and then was moving as fast as the first one, and then it was moving faster and faster. It gained more speed. So this is actually a non-uniform. So this is still uniform motion, similar to the first one. So the acceleration is actually 0 in this case too. But the acceleration here, this is non-uniform. As a matter of fact, it's uniformly accelerated, and the acceleration is positive because it's gaining more and more speed in this case. Okay, and at some point between B and D, it's moving with the same speed as car A. Okay, so this is basically what I plan to share with you guys. I really want you guys to focus on the assignment and go through it thoroughly, because part of the questions that you will be having down the road in exam 2, they will be quantitative. They will be actually not just questions. So you will be actually working problems and solving questions and doing answers and things like that. Because the first assignments, you are not required to submit them for grading. This one is actually required for grading, so you're going to submit it. And also the next homework assignment, which will be a little bit more calculations in it than this one, honestly. So I'm hoping that you guys will get into the habit of doing these things, and the next time you'll also be going to be graded, because coming exam 2, which is not too far from now, we need to really be ready to doing this type of assignments. Sounds good? Okay, so I'm going to stop the recording, and I wish you guys to go through the preparation as much as you can for the exam, and I will see you guys Monday, both for lecture and lab, okay? Yes? Okay, I'm gonna stop the recording. I'll see you guys.